Hello everyone. In this lecture we will learn about atomic absorption and emission spectroscopy. Introduction. The atomic absorption spectroscopy, AAS, and atomic emission spectroscopy, EAS, is a spectroanalytical procedure for the quantitative determination of chemical elements. It uses the absorption of optical radiation by free atoms in the gaseous state. Atomic absorption spectroscopy is based on absorption of light by free metallic ions. The technique is useful in determining the concentration of a particular element, given analyte, in a sample to be analyzed. Atomic absorption methods measure the amount of energy, in the form of photons of light, and thus a change in the wavelength, absorbed by the sample. History. The modern form of AAS was largely developed during the 1950s by a team of Australian chemists. They were led by Sir Alan Walsh at the Commonwealth Scientific and Industrial Research Organisation, CSIRO, Division of Chemical Physics, in Melbourne, Australia. Process of atomic absorption spectroscopy, AAS. The process of atomic absorption spectroscopy, AAS, involves two steps. 1. Atomization of the sample. The sample, either a liquid or a solid, is atomized in either a flame or a graphite furnace. 2. The absorption of radiation. The absorption of ultraviolet or visible light. The free atoms undergo electronic transitions from the ground state to excited electronic states. This diagram shows a basics of atomic absorption and emission. Light of a specific wavelength is absorbed by the electrons of atoms of given compound when the atoms excites, and a specific wavelength is released when the electrons goes back to the original state. Instrumentation for atomic absorption spectroscopy, AAS. Atomic absorption spectrometer needs the following three components. 1. The light source. The common source of light is a hollow cathode lamp. This contains a tungsten anode and a cylindrical hollow cathode made of the element to be determined. These are sealed in a glass tube filled with an inert gas, e.g. neon or argon, at a pressure of between 1 nm2 and 5 nm2. The ionization of gas atoms occurs by applying a potential difference of about 300–400 V between the anode and the cathode. These gaseous ions bombard the cathode and eject metal atoms from the cathode in a process called sputtering. 2. Sample cell to produce gaseous atoms. Sample preparation is often simple, and the chemical form of the element is usually not important. This is because atomization converts the sample into free atoms irrespective of its initial state. The sample is weighed and made into a solution by suitable dilution. When making reference solutions of the element under analysis, for calibration, the chemical environment of the sample should be matched as closely as possible. 3. A device for measuring the specific light absorbed. The device is used to detect the amount of light absorbed. A calibration curve is used to determine the unknown concentration of an element, e.g. lead in a solution. The instrument is calibrated using several solutions of known concentrations. A calibration curve is produced which is continually rescaled as more concentrated solutions are used. The more concentrated solutions absorbs more radiation up to a certain absorbance. A generalized diagram of atomic absorption spectrometry, which consist of 1. Sources of light, 2. Chopper for material reduction, 3. Flame for exciting the atoms to higher energy state, 4. Monochromator, 5. A detector for detecting light, 6. A meter to measure the absorption. Application of atomic absorption spectrometry. 1. Clinical analysis. Analysis of metals in biological fluids like blood and urine. Atomic absorption spectrometry has many uses in different areas of chemistry, such as clinical analysis of metals in biological fluids and tissues such as whole blood, plasma, urine, saliva, brain tissue, liver, hair, muscle tissue. 2. Environmental analysis. Monitoring our environment, e.g. finding the levels of various elements in rivers, seawater, drinking water, air, and drinks such as wine, beer and fruit drinks. 3. Pharmaceuticals. In some pharmaceutical manufacturing processes, minute quantities of a catalyst used in the process, usually a metal, are sometimes present in the final product. By using AAS, the amount of catalyst present in final product can be determined. 4. Industry. Many raw materials are examined and AAS is widely used to check that the major elements are present and that toxic impurities are lower than specified. 5. Mining. By using AAS, the amount of metals such as gold in rocks can be determined to see whether it is worth mining the rocks to extract the gold. Atomic Emission Spectroscopy. Atomic Emission Spectroscopy, ES or OES, uses quantitative measurement of the optical emission from excited atoms to determine analyte concentration. Analyte atoms in solution are aspirated into the excitation region where they are desolvated, vaporized, and atomized by a flame, discharge, or plasma. These high-temperature atomization sources provide sufficient energy to promote the atoms into high energy levels. Atomic Emission Spectroscopy, ES or OES, uses quantitative measurement of the optical emission from excited atoms to determine analyte concentration. Analyte atoms in solution are aspirated into the excitation region where they are desolvated, vaporized, and atomized by a flame, discharge, or plasma. These high-temperature atomization sources provide sufficient energy to promote the atoms into high energy levels. History. Atomic emission spectroscopy was first used as an analytical technique, and the basic principles were established by Robert Wilhelm Bunsen and Gustav Robert Kirchhoff, both professors at the University of Heidelberg, Germany. Instrumentation. 1. Sample introduction. Liquid samples are nebulized and carried into the excitation source by a flowing gas. Solid samples can be introduced into the source by a slurry or by laser ablation of the solid sample in a gas stream. 2. Excitation. The excitation source must desolvate, atomize, and excite the analyte atoms. A variety of excitation sources are described here. A. Flame. A sample of a material, analyte, is brought into the flame as a gas, sprayed solution, or directly inserted into the flame by use of a small loop of wire, usually platinum. The heat from the flame evaporates the solvent and breaks intramolecular bonds to create free atoms. The thermal energy also excites the atoms into excited electronic states that subsequently emit light when they return to the ground electronic state. B.Arc/spark. Spark or arc atomic emission spectroscopy is used for the analysis of metallic elements in solid samples. For non-conductive materials, the sample is ground with graphite powder to make it conductive. C.Plasma. Plasma atomic emission spectroscopy, ICPEs, uses an inductively coupled plasma to produce excited atoms and ions that emit electromagnetic radiation at wavelengths characteristic of a particular element. A diagrammatic representation of atomic emission spectroscopy is given here. It consists of following parts. A excitation source for electron excitation. A lens for focusing the light. A wavelength selector for selecting a specific wavelength. A detector for identifying emitted wavelength of light. Applications. Atomic emission spectroscopy have found application in many areas of materials science. The electronics industry requires materials of high purity and hence there is a need to monitor trace impurity levels in materials used for electronic components. As a consequence, various techniques of atomic spectroscopy have been applied to the analysis of materials used in the manufacture of electronic components. Thank you all.